So far, we've looked at some basics for thunderstorm formation in northern Arizona. In stage C4, we looked at convective uplift and stability over just a flat region. In C5, we looked at calm days leading to upslope winds along mountain slopes and how topography is one of the main catalysts for cloud and storm formation in northern Arizona. But if you've been running around the game, the Lightning game here, you might have seen that some locations don't have topography around them as a main factor that could have led to the lightning strike clustering. And so one example is Donny Park right here in the game, where you can see it's a pretty tight cluster of lightning, and there isn't really raised topography nearby. So how does this get here? How did this lightning get here, aside from basic just convection rising off of the surface? And that's caused by steering winds in the atmosphere. So as air rises up, it's going to get picked up by winds aloft and carried around the landscape. And so when we're looking at question C6, we're looking at these steering winds, how clouds are getting moved, how storms are getting moved based on the winds in the atmosphere, and how we can have these clusters of lightning, even though there might not have been any topography nearby, directly nearby, that kicked it off. And so for this example, we're using Donny Park, and we're going to talk about an area south of Donny Park. If we have strong southerly winds, which we sometimes do during monsoon season, that are going to lead to lightning striking at this location. So for question C6.1, we're wanting to know what the dew point, we're trying to figure out the atmospheric conditions necessary. If we're at Donny Park and we want to know what conditions were present that led to these lightning strikes at Donny Park. So we're going to start at Lake Mary and Anderson Mesa, which is just above Lake Mary. So let's fast travel to Lake Mary real quick. Okay, so here's Lake Mary. It's a pretty fun place to explore and climb and hike, just to the southeast of Flagstaff if you're ever in the area. And then Anderson Mesa is the raised cliff just to the north of the lake right here. And so we're wanting to know in this question, 6.1, what the dew point would have to be where we're standing at in Lake Mary in order for clouds to form 800 meters above Anderson Mesa. So in order to solve for this, we need to take the atmospheric conditions at Lake Mary. We need to figure out the air temperature and the elevation at Lake Mary. So we have 24 degrees Celsius, and we have a height of 2,065 meters. And we want to know 800 meters above Anderson Mesa. So let's run to the top of Anderson Mesa. Okay. And we're saying winds from the south are going to be kicked up along this ridge. And we want to know what the dew point would have to be for clouds to form 800 meters above this point, if it's lifted orographically. Okay. So this elevation is at 2,185 meters. So 800 meters above that would be 2,985 meters. So that's the height of our lifted condensation level. That is the point that the cloud base is forming in this example. But now we need to figure out the dew point. So in order to calculate the dew point, we're going to use this equation. Okay. So we have our starting temperature, and we need to figure out the elevation change. So the elevation change between Lake Mary and the lifted condensation level is 920 meters. So in order to calculate the dew point, we need our starting temperature, which is 24, minus our elevation change, but we're going to convert that to kilometers because our lapse rate is going to be using degrees Celsius per kilometer. And the lapse rate we're going to use is the dry adiabatic lapse rate, or 10 degrees Celsius per kilometer. The reason we use dry instead of wet in this example is because we're not saturated yet. We're not at dew point. And so that's going to be 10 degrees Celsius per kilometer. And so overall, our dew point is going to end up being 14.8 degrees Celsius. That's how humid the atmosphere would have to be in order for clouds to form 800 meters above Anderson Mesa. Okay, so for question 6.2, we want to know how long it's going to take from our cloud base at 2,985 meters, how long it's going to take for the cloud to grow to a height of 10 kilometers. The reason the cloud needs to get tall enough is because there needs to be enough collision within the updrafts and downdrafts of the storm between water and ice particles to build up enough static charge for lightning to occur. It needs to reach the mature stage of the thunderstorm. If it was smaller than that, we might not have enough capability for the storm to create enough static electricity within it to create lightning. So we're going to say 10 kilometers tall. Okay, and so in order to solve for this, we just need to figure out the difference in elevation between our elliptic condensation level and the top of the cloud. So we're basically finding the height, the thickness of the cloud. In order to do that, we just need to do 10,000 meters minus 2,985 meters, and that's equal to 7,015 meters. And we're saying that with updraft winds of 300 meters per minute, how long is it going to take for our thunderstorm to reach maturity? How long is it going to take for it to reach 10,000 meters, 10 kilometers in the atmosphere? It's a pretty easy question. We'll say 10 kilometer time is equal to the distance, thickness of the storm divided by 300 meters per minute. Okay, that's our updraft speed. And we calculate that, that's equal to 23.4 minutes. All right, and that's a pretty typical case for thunderstorms in northern Arizona during monsoon season, about 20 to 30 minutes for a mature thunderstorm to form from that original updraft, that original upkick from that Anderson Mesa. Okay, and then the last question, 6.3, we're wanting to figure out if we're standing at Doney Park and we see clouds bubbling up to our south, we want to know how fast the winds are steering the storm to this location, figure out why we have so many lightning strikes here. So how strong are the winds that led to these lightning strikes if the storm started at Anderson Mesa and it reached maturity in 23.4 minutes? Okay, so in order to solve for this, we need to convert, we're going to solve for kilometers per hour. Okay, so we're going to give you in Canvas the distance between the two locations. So in this case, the distance between Anderson Mesa and Doney Park is 14 kilometers. Okay, so all we're trying to figure out then is our wind speed in kilometers per hour. So we need to convert our time that we have 23.4 minutes into hours, and that's equal to 0.39 hours. We just divide it by 60 minutes in an hour. And then we just take our distance over time, so 14 kilometers divided by 0.39 hours, and that's equal to roughly 35 kilometers per hour, or about 21 miles per hour for our steering winds. And that's pretty typical on a windy monsoon day in northern Arizona, at least above the surface. So in this case, we looked at how we can get storm formation if there's wind during the day. How steering winds can influence the lightning strikes that we see across the geovisualization.